3, 2, 1. Alright, so we've now got that the lower and upper Darboux sums are respectively the supremum and the other way around, the infimum and the supremum of the Riemann sums. So we want to now, of course, introduce the notion of mesh, which again was our sort of, hey, this is how we did it in calculus, and of course make a nice epsilon delta type setup here. So given a partition, we'll define its mesh to be, indeed, the maximum of all of the lengths of the subintervals. And now we have all the ingredients we need to set up a epsilon delta style setup for the Riemann integral. So indeed, given an epsilon, there is a delta, so that any partition whose mesh does not exceed delta, the Riemann sums are within epsilon of our proposed I, and thus if you have this exact setup here, then you are indeed Riemann integrable, and your integral is in fact equal to this value I here. Alright, great. So here we go, our first epsilon delta sort of setup. So let's work out the details. So given an epsilon, that means that by our hypothesis here, we can always find deltas so that partitions whose mesh does not exceed delta, the Riemann sums, get within the epsilon of the I. Alright, so again, note this is the sort of the converges to a particular real number. Alright, well, so by hypothesis, that means that since for any epsilon we can find a delta so that any partition whose mesh does not exceed that delta, life is working. Alright, well, the epsilon here we're choosing is 1 over 2n, probably because I'm going to have, like, an upper and a lower, so I'll have two things, so, just prepping for that. And we have these deltas that work. Alright, great. Okay, so note, the Riemann sums get within I, and, I got some delta n's here. Let's get working. Okay, so, in particular, note that for any n, we have these delta n's which are positive, and if we look at the ratio of those delta n's divided by the length of the subinterval, that's some positive number, and I can always find a 1 over a natural number that gets smaller than it, and so I'll have these m sub n's like this, and the reasoning for these will become apparent, hopefully, in a few slides here. Now, note that these 1 over n's that I made, I can now do the uniform partition. Note that this is being rigged so that this partition that I'm making is going to get a mesh size no bigger than delta. So I can now create this sort of a uniform partition, which we saw in action when we were directly computing the Riemann integral of the function f of x equals x. Right, and note this thing is rigged so that all of its subintervals are all of the same length, and it is indeed a partition. And note that all the subintervals are just b minus a over whatever this m sub n is, and again that's chosen so that this gets less than the delta n, so that my partition here that I've made is within delta, meaning that I've got things within the appropriate epsilon that I already set up, which in this case was of course 1 over 2n. Alright, so I've created now a partition where these things work. It's uniformly spread out, so obviously I'm going to now show the upper and lower Darboux sums are behaving nicely. Alright, now to make that work, of course, let R be the collection of the Riemann sums on this partition M sub this partition P that I've created. Recall that the Riemann sums are in fact the infimum and the supremum of these things. Alright, which, and then by construction, we noted that I is within 1 over 2 to the n of this thing, so when I look at this difference, that's bigger than negative 1 over 2 to the n. And from that gives me that I minus 1 over 2 to the n is strictly less than this thing here. And that's good for any choice, and so that means I minus 1 over 2n is a lower bound for the Riemann sums, which means that it is less than or equal to the greatest lower bound, which is the Darboux sums. Right, and then a similar thing happens for the upper Darboux sums, and hey, wouldn't you know it, I have constructed a Archimedean sequence of partitions. So the uniformly spaced partition comes to the rescue, gives me that I am indeed Archimedean, and now, as we take the limit, we know that this will ensure that I'm Riemann integrable, and that the limit of those things will be the original integral. But note how these things are set up is that when I take the limit of them, they're bounded above by I, and bounded below by I. So they have to equal I, and there we go. You are indeed Riemann integrable, and your integral is the I from our hypothesis. So given an epsilon, we found a delta, and now we have gotten, hey, a limiting version of the classic calculus approach. All right, but I'm not done yet. Oh no. Because now I'm going to do you one better. So that gave you a, given an epsilon, there is a delta, then we know that your Riemann integral, and your integral is within, and your integral is what you would expect it to be. But we're going to give a sort of more improved version of that with the following. So that gave you a condition to ensure you were Riemann integrable. Now let's go in reverse. Suppose you are Riemann integrable and you have an epsilon. Well, I would love to find a Riemann sum that gets within epsilon of my integral. So this one note is working kind of in reverse. Before, I was proving that given an epsilon, there's a delta, so the Riemann sums are going to behave. Well, now, suppose I have my Riemann integral. I want to show that Riemann sums can be chosen to be within epsilon. So, in other words, what we're proving now is if I have something Riemann integrable, its Riemann sums do in fact approximate the integral. There we go. So, while the previous proposition gave us the epsilon delta characterization to ensure integrability, this here is revealing that if you are integrable, then Riemann sums will in fact approximate the value of the integral. Alright, so let's actually go ahead and prove this. Alright, so again, note the difference between this and the previous. Here, I'm assuming Riemann integral. The previous one was demonstrating Riemann integrable. Alright, great. Okay, so let's go ahead and prove this now. So if you are Riemann integrable, your integral is in fact approximated by your Riemann sums. Okay. So, given an epsilon, I want to find a delta. Alright, now, as we are Riemann integrable, we know we can find partitions so that the upper and lower Darboux sums get within epsilon. So that gives me a partition to work with. Okay. And our function's bounded, so there is some b, so that my outputs f's don't get any bigger than b at absolute value. And obviously, I'm going to let the delta that I'm looking for be epsilon over 4b times n plus 1. Clearly, right, this is rudimentary. Right, so this delta descends from the sky. Yeah, it's pretty great. Right now, obviously, it's not clear at all why this is going to be the correct delta, but trust me, bro, it is. And there's a 4 down here now, because you know, why not? Alright, so I claim this is the delta we need to ensure that, given an epsilon, any Riemann sum whose partition's mesh is bounded above by delta strictly is going to get within epsilon of the integral itself. So, thus revealing that if we know we are Riemann integrable, the actual value of the integral can be approximated using Riemann sums. Okay. And now note, actually, this vaguely gives you what the delta needs to be. But basically saying that, given epsilon, once you get your mesh size small enough, then your Riemann sums get within the integral. Alright, so take a partition whose mesh size is bigger than delta. I want to show that we are within epsilon of the actual Riemann integral. Alright, so I'm going to claim that this holds, and that it's going to basically get us what we need. Alright, now note basically everything is constructed to ensure this happens. Now, what do we need to do? So, before we get going, let's remind ourselves of some symbols here. So, we started off with some partition R, so that the upper and lower Darboux sums are within epsilon over 2 of each other. And that partition R is going to be indexed using y's. We've now picked a partition P, whose mesh size is strictly less than delta, and I claim that things are rigged, so these would be less than epsilon. Alright, so what I need to do now is basically compare this partition P to this partition R, because we already know this partition R is going to behave nicely. So it's going to be very similar to what we had done before, which is, alright, well, let's look at the points that don't land where we want them to land. So these are the points out of the original partition R that aren't landing in the subintervals accordingly for the partition P. Okay. Right, and note that for any element out of this set where these elements Y are not landing in the subintervals, well, they're missing a subinterval, which means that the subinterval from x is going to be contained within the subinterval for the y. All right. So we had this partition that we started with that got us the upper and lower Darbosomes with an epsilon over 2. We are now picking a new partition, and what we're doing is kind of looking for the exceptional sort of things, the points that don't belong to the subintervals, and if they don't, that means that their corresponding subinterval contains these other subintervals. Right. And note here that the delta for x does not exceed the delta for y. And again, the y was the original one that was picked, and the x is the new one that we've made. All right. Okay. And note here that by sort of how we similarly did this before, where we had a partition and we were comparing it with another one, here we'll get that the infimum on the Jth subinterval of the partition R does not exceed the kth subinterval partition P, right? That's just coming out of, we know that this one is the bigger interval, right? So the infimum can only get, excuse me, right, can't get any bigger, right? So it has to, right, either equal it or maybe it got smaller because we, right, threw away more stuff. And likewise for the soups. All right, and then from there, if we were to look at the sum of the differences of these things, note that these here, since all of these are bounded by the soup and the inf for the the soup and the imps from the partition R, which was the original one, right? The sum of all these things won't exceed epsilon over 2. Again, these were chosen, so this was less than epsilon over 2. All right, so all of the indices of the original partition, which contain the subintervals, right? So they themselves did not land in any of the subintervals. That sum, though parts of those will be less than epsilon over 2. So now we just got to take care of the ones that actually do work. Right. Now, for the ones that do work, this means that each of the original partition elements landed in one of the new subintervals. And this one had n elements, so this set, exceptional set C, has at most n plus 1. All right, and B is bounded below and above by B, so we know that when I take the difference of the soups on these subintervals, they aren't going to exceed 2B. And since the mesh size is strictly less than delta, when I look at any one of the soup minus the inf times the delta, the width of the subintervals, well, all right, I'm going to, right, all of these are bounded by 2b, so these will be 2b times delta. All right, and now hopefully you're seeing where the 4b is going to show up. The 4 is going to pop in, because now when I look at the sum of all of these things, well, right, there are at most n plus 1 of them, so I have 2b times delta times n plus 1, and note that was rigged to give me epsilon over 2. That's why there was the 4 down there, to give me the epsilon 2, because I was going to have twice of these things. Oh, there you go. All right, so now when I look at the upper and lower Darbosomes difference of the partition P, that splits into the elements whose subintervals were contained in the original subintervals, and then the elements who were not contained in those subintervals, but rather contained the points. And we've argued that both of these things add up to no more than epsilon. And so here we go. We've now got the upper and lower Darbosum to be within epsilon of each other. And finally, then, if we go ahead and create a Riemann sum, it's going to have to live between the upper and the lower. And that means now when I look at the integral minus this Riemann sum, well, in absolute value, the difference apart from these cannot be any more than the difference of this and that was rigged to be epsilon. So, there we go. We've proven that now if you're Riemann integrable, then given an epsilon, there is a mesh size, ensuring that any Riemann integral gets within it. Pretty nice. Alright, so with all of that, we have now formally set up everything that you're going to need for the Riemann integral and how to work with it using traditional Riemann sums, and also using these fancier Darboux sums. So obviously, now that we have all of these tools at our disposal, I want to, prove the Riemann integral behaves the way I expected it to. So it's got some classic properties, which we'll get into next.